Hello! Today we are taking the prototype from last time that we used numpy and we're converting it to a Python that uses for loops so that we can convert this more easily into Java so that we can put it into an app, because we will not have access to numpy when we go write an app out of this. So the first item we're going to do here is we're going to take this file from last time and we will just save it as a different file name. We'll say test2.py. Okay. The other item we need to do is, so we will create a class. We will say class, we'll call it Node Fourier Transform. So the init function will have self, of course. Self is the thing that is this pointer for the class. Sample rate. This is the default. We'll put 44100. Smoothing is 4096. Now smoothing is just our window size that we are going to average over after we downshift step. And that's 0.1. And then note min equals, we'll go from MIDI node 24, node max, actually node stop equals, and then we do, for that one we'll put 120 just to account for the harmonics. I know we did 108 earlier, but we'll account for harmonics. Self.sample rate, we just copy some variables over into self, and I kind of want a blank line there. Sample rate, so it'll take the sample rate here, it'll copy it into self. Then we have self.smoothing equals smoothing. Then we have self.node step equals node step. Self, we're just copying things. Now, all the things are copied, but we do need to do some other initialization in here as well. We'll do the dt 1 over sample rate. And then we will also we'll create the note list as we did last time, which is this right here, but we'll use the variables instead. numpy.arange. We'll do multi-line so that you can see all of the line. So from the minimum node to the stop, and node step, and then we'll do, I think Python might even need a backslash there, but we do dtype equals, so we tell numpy what type to use. We'll use float 32 for these because we don't need a lot of accuracy. So we can do node to freak, self.node list, and this will also be a float 32. So the phase list we will use as the, kind of like the phase list here, but we will use it, we will initialize everything to 0, and instead of using the timestamps, we will use the dt and the frequencies to update it. So we will take a slightly different approach in the class here, because we need it to be more, we need to be able to take some samples of audio data and just dump it into this class and have the class process it, then dump more samples, just arbitrary numbers of samples, and the class should process everything just continuously. So what we are doing here is, instead of bothering with, oh, what is t, what is really just what is t and what is phi naught, we just call this phase list. This is just going to be the running phase, and then instead of using 2pi ft, we will use 2 pi f delta t. So that way we use the timestamp to increment the phase of each one, and of course that also depends on the frequency. So we don't have to worry about absolute times, we only have to worry about how much the phase changes in each step of the way. So that's what we're doing here with this phase list. We'll use that different approach. Keep in mind that the result is going to be complex because this is the result of a Fourier transform, essentially. And the complex vectors will contain not only the magnitude or amplitude, but also they will contain the phase. And the phase that we're talking about is the phase of each wave. So if there is, say, a 10 kilohertz wave in there, we need to know what phase it is as well. So we don't necessarily need to know, but it will be there just because that's how the transform works. And we can't just solve for the amplitude, we have to solve for the amplitude and phase, and then we just can extract the amplitude from the result. It's just how math works. So what we've done here is we'll be using the result samples to contain the intermediate result. What it will have is it will have the downshifted sound waves. So all we have to do with the result samples then, in order to obtain the graph from before with the peaks like this, is we will simply need to take a sum over the result samples over the smoothing axis. So what we have is we just store everything in an intermediate buffer, but it will also be a rolling buffer, so we will fill it from the beginning to the end, but when we come to the end and we have more data to fill, we will start again at the beginning and we'll keep going. It's a circular buffer. The result counts here will count how many samples have been written to each particular frequency bin since the last fill, and the result fills will count how many times this particular frequency bin has been filled with samples. So we will use these two, particularly the fills, to determine which of the frequency bins we can already use and which ones haven't been filled yet, where the number of fills is 0. So if it hasn't been filled yet, it means we haven't collected enough samples to know the answer yet. So the write function, it accepts some samples, some sound samples, and we will go through, and for each frequency we will update the result numbers. So here you see that we take the input sample and we downshift it by the phase. Of course, the phase increments by 2 pi f dt. And that's nothing new. It's just before we were using timestamps, whereas now we're using the delta time. The count counts which sample we are looking at right now for this frequency bin. Now we have some logic to do wraparound. Now when wraparound happens, we need to, so if the count reaches the smoothing number, we can't put more items into result samples because that exceeds the size of the buffer. So we need to put the count back to 0, but we count the fills. And last but not least, we need to update the numbers for this. So this function write, it will update the result samples buffer. Now, in order to obtain the result that we had in the last video we need to create another function that takes the sum over this. What we've done is we've done effectively the same thing. So result samples is the same as product over here. So we did product.sum axis equals 1. Same thing here, result samples.sum axis equals 1. Now this is kind of interesting because with the result fills, so if we haven't filled the buffer yet, then there is no point in taking the average. But if we filled the buffer at least once, then there's enough samples in there that we can take the average and we can expect it mostly to be smooth. So that's what we do here. We see which ones haven't been filled and we set the sum there to 0. And then the result is of course the same as we had before. Here we had the freq pow. The power is the absolute frequency coefficient squared, and we do the same thing here, absolute result sum squared. Now the frequency coefficient is the axis sum. So basically we have the same things here. The only thing that changes is from node list up all the way until here. We backspace. Okay, so we need to define freq pow. But before we even do that, we need to do ft equals node ft, and Python kind of helps us a little bit here. Sample rate equals sample rate. So we're setting the sample rate to this sample rate, and then smoothing equals 4096, just as usual, even though that's the default value. Let's see, are there any other parameters we want to change? The others are just these. We'll leave them at the default values there. ft.write samples, and we'll put 0 through 40, 0 through ft.smoothing. So that will give us the first 4096 samples. We'll just dump those samples in. We won't worry about other things right now. And then we need to call the result function to obtain the power. Now the node list, actually, so ft.node list, we can do that, we'll take the notes from there. And what I realized actually is I forgot to update, so this should be a note, which is meaty number. So I forgot to update the label, and then this should be power instead of amplitude at this point because we squared it. So let's see if I didn't make any mistakes. Then maybe let's rename this old spectrum just so that in case it's the same we. So what is spectrum? Whoa, okay. What did I do here? Trying to figure out what's different between. This looks like the. I think it's the. Oh, I think I know. Instead of 4096, I think it's 8192 is the better one. Let's try that. Because the thing is, if you set it to, and that's the old one, if you set it to a number that is too low, then the averaging won't work as well, and so you'll have a lot of these big widths. Now, as you can see, this is running a lot slower, and it is ideally doing the same thing. But with for loops, you run a lot slower in Python. That is why you use numpy arrays when you can, and you use broadcasting because those are pretty much like there are procedures written in binary, like in C, that do that for us. Whereas if we use a for loop in Python, so same chart. Now, what I want you to notice is this. So this little bump here, it is very difficult to notice. But the other thing that I was wondering about is when we have a wavelength that is, say, very small, then that means a high frequency. So we have a lot of periods that we're summing over. Whereas if we have a long wavelength, then that's only a few periods that we are summing over. So I'm just wondering, I'm just wondering if we can make this bump a little bit more visible. So let's go into the code and let's try over here. Let's put this expression into parentheses. And then, so yeah, like that. And then we'll take the result samples and we'll divide it by self.freqlist.reshape -1,1. So let's see if that gives us any different results, because here I just divided by the frequency that, so each of these peaks, I'm just dividing by what frequency it is. So the higher the frequency, the more we're going to divide it by. And the other thing that this will do for us is it will make it so that the fundamental frequency is more likely to be prominent. So let's go try that. All right, it's done. Let's go see the result. All right, okay, so we do see this peak a little bit better. And we do have some noise down here, which is fine. The important point is that now we can search for this peak, and this is our fundamental frequency for this note. And then this one is an octave higher. This one is maybe a quinta higher. I'm gonna have to check, I'm not entirely sure. But, so we're looking so far so good. And another way that we could have written it is using this other notation, which is result sum times result sum conjugate. That is equivalent to the absolute value squared, and then we take the magnitude of that. So that also gives us a very similar graph. Well, all right, so that was how we convert Python code that uses numpy into Python code that does not use numpy, so that we can more easily translate it into Java or another language that is app friendly. Next time we can overlay a graph that shows a keyboard with this so that we can see where the piano keys are. See you next time, and thank you for tuning in.